What is up, everybody? Juan here, and today we're going to talk about the mystery question that a lot of people bring up. Why are we stronger during the eccentric phase of a lift? Have you ever seen or have you ever experienced that when you, for example, let's do a bicep curl, when you ever do a bicep curl and you curl the weight, it's a lot harder to actually lift the weight than to actually lower it or to lower it. Or have you seen people do like these types of exercises or reps where they have their friend or where they pick a really heavy weight, probably more than they can lift or concentrically lift, and they have their friend help them skip that concentric part, but then they could lower it by themselves during the eccentric phase. Now, how is this possible? Why can our muscles just produce more force during this lowering phase of a muscle? Well, today we're going to talk about this. And we're going to go over muscle structure first because muscle structure is very important here. You must know how the muscle is structured in order to understand this theory onto why we are stronger in the eccentric contraction. So after we learn muscle structure, we're going to go into the cross bridge cycle. The cross bridge cycle is the key here into understanding this phenomenon, into this answer on this eccentric strength or eccentric force production. Then we're going to talk about the contractions, right? The concentric contraction, the eccentric contraction. What is the difference and what is the difference in force, or what causes the difference in force between these two contractions? And we're going to end with a conclusion. So first things first, muscle structure, keeping it very simple here. Here we have the muscle, right? We have the entire muscle where you can see the tendon, the bone, and then we can see the muscle that's going to open up and we're going to cut it into little pieces, right? So we have the entire muscle here and it's surrounded by this paramecium, right? And you see these things inside of that muscle, right? These compartments, right? These are fascicles, right? So we zoom in, we get a fascicle. And in that muscle fascicle, that's made up of other smaller compartments called the muscle fibers, right? Or the muscle cell, right? And that muscle cell, if we zoom in even more, is made up of even smaller compartments called myofibrils. And inside of these myofibrils is what contains these force generating proteins, myosin and actin, and these are the myofilaments. And this is what we're going to get into when we talk about these contractions and this force production. Okay, so here we're going to go back in time a little bit, back to 1957, where a famous scientist known by the name as Andrew Huxley believed that we have cross bridges on the myosin filament. The myosin filament is that thick bar you see on the top, well, where it says myosin filament, right? He believed that these cross bridges will interact in a cycle type motion with certain attachment sites on the actin filament. The actin filament is that thin filament or that thin bar below the myosin filament right there, right? So he assumed he assumed that this can happen based on rate constants of attachment. And we're going to get into that a little later in the slides. But basically, the probability of the cross bridges attaching to the nearest attachment site is governed by these rate constants. So it's very interesting. It sounds complicated, but once we get to the bottom of it, it's actually going to be very simple, right? So we also see in this picture, there's an equilibrium position of the M site, right? And then there's an X, which shows two arrows. So let's talk about the X first, which is very important as well. As you'll see, the X here has an arrow pointing in two directions, one on the left, one on the right. On the left side of the X, we see that vertical line with the dashes. That's the equilibrium position right? In the equilibrium position, the spring that is attached to the cross bridge at the M site carries no force. It's relaxed, right? And on the right side of the X, we see the attachment site or a attachment site, right? However, we notice that the M site here, the cross bridge, is a little more to the right, since is a little more to the right of the or is moved a little more to the right. And if you see that the springs or those springs or those links, the right spring, it looks like it's much bunched in together, more crunched in, but the left spring looks like it's being stretched apart, right? And the idea is that these springs are linear, right? Now, the force gets bigger the greater the x distance. What does that mean? So because these are linear springs, or because these are linear springs, as the x distance increases, as the distance of that equilibrium position from that attachment site begins to increase, the force is going to get bigger, that spring. So as you notice, the left spring, that link right there, it's being stretched apart. The more that stretches apart, the more force is going to occur, the more force is going to carry, right? What's interesting though, and don't get scared, uh, this is a more modern take on it, right? So what's interesting is that, well, I use the bicep in this example, and the bicep has a unique length tension curve, which is why we're going to see optimal overlap when the muscle is fully or almost fully extended. Now, here we have two positions of the limb. We have one where the arm is fully extended or near fully extended, and we have one where the arm is fully flexed, right? Now, when the arm is fully extended, we see that the bicep muscle is being stretched. And here we can see the optimal overlap of these cross bridges, right? So we see the myosin having optimal overlap, where the myosin is being represented by the orange structure. It's having optimal cross bridges with the actin, and that's going to be represented by the purple structure, right? The purple structure on top of the orange and below the orange, right? And here in the optimal overlap, we see the most amount of cross bridges occurring. However, when we see the fully shortened bicep, we see that there's too much overlap, right? This is going to decrease the amount of force that the bicep can produce. Now, on the far right of the picture, we can see a more zoomed in aspect of we can see more zoomed in of what's occurring. And we see like these red balloons, these globular heads of the myosin, these cross bridges. And you can see them attaching to the actin, which is represented by the purple. Now, don't freak out here, all right? You see math, don't freak out, all right? What's interesting is that Huxley was the first to express this cross-bridge theory in mathematical terms. To me, that's super interesting. Now, we're not going to get deep into this, but this equation is one of the simplest ones that he put on there, but they do get much more complex the more you begin to look into them. So we're not going to get into them, but it was just cool to let you guys know that this cross-bridge theory can be represented by mathematics. All right, so now we're going to get into the contractions, right? The interesting part, the answer, right? That's what we're looking for. So in this graph, we see a lot of letters, a lot of symbols, and they all represent something, right? And it's important to know what they represent in this graph. So starting with the x. The x refers to the distance between the cross bridge's resting position, which is the equilibrium position, and the nearest eligible binding site, right? The f refers to how fast cross bridges attach from actin. The G refers to how fast cross bridges detach from actin, right? So they can attach and then they can detach, right? It's more like a hook and pull. There is some rotational aspect, kind of like a corkscrew. So it is kind of interesting. So the F and the G are referred to as the rate functions, right? As the rate constants. So these are the things that govern the probability of the attachments, of the cross bridges attaching to an attachment site, right? The H plus represents the maximum range of possible cross bridge attachments to actin. And these attachments and detachments are entirely dependent on the X value. So pay attention to that X because that's where our answer is going to lie in. Now, why is this important? Well, we know that the overall force in a muscle depends on the number of attached cross bridges multiplied by the average force per cross bridge from its equilibrium position, which is represented by the distance of x. Right? We could see the distance of x right there, pointing and having its arrows pointing in its two directions. It's between the myosin and actin filament model and the graph representation of the graph model of G and F. Between those two models or pictures, there's the X constant. Now, if you look to the right on the actin filament, we see there are arrows, one arrow pointing left, one arrow pointing right. The C pointing to the left stands for the concentric contraction, or the movement of the actin filament during the concentric contraction, and the E stands for the movement of the actin filament in the eccentric contraction. Now, let's talk about eccentric contractions first. Let's talk about the concentric contractions first. If the actin filament moves to the left, the X distance will become smaller, right? If we're moving the actin filament this way, we notice that the distance of X is going to decrease. And therefore, the force in the left spring element becomes smaller. So we notice that the spring on the left is kind of like stretched apart, while the right spring is more crunched in. That the spring element that's more kind of like spread out is going to begin to get more crunched in or scrunched in. And that means that the force in that spring, or the force that that spring is going to carry, is going to decrease. Right? So in the concentric contraction, you are continuously decreasing the force available to the cross bridge. On top of that, however, the rate constant of detachment, which is represented by G, when you shorten, it begins to move up on the y-axis to about 4, which is pretty high. So the cross bridges detach very quickly in a concentric contraction. Right? So because the rate constant G, which here we refer to as how fast the cross bridges detach from actin, is moving up during a concentric contraction on the y-axis, that is going to indicate that the detachment rate is going to be very high, or very quickly. Yeah. However, during an eccentric contraction, it's the complete opposite. The opposite is occurring, right? If the actin filament begins to move to the right, right? If we get the actin filament and we begin to move it this way, how the arrow is indicating, the X distance will begin to increase. It's going to increase, right? That means that the force in cross bridges that are attached will tend to increase. And here, the detachment rate constant G is relatively small. Therefore, the detachment rate, or the detachment, is going to be relatively slow, right? So the simple answer to the crossbridge theory onto why, or according to the crossbridge theory, onto why the eccentric is stronger than the concentric in terms of force production, is that eccentric force is greater than concentric force, is going to be due to the fact that N, which represents the proportion of cross bridges, is greater, and X, which represents the amount of force in a cross bridge, is greater as well, or is bigger. And this is why eccentrics are better than concentrics in terms of force production. So that was all for this PowerPoint. Nice and quick. Hope you guys are able to understand next time why you're able to lower a lot more weight than you can lift. As always, make sure to like, subscribe. You can follow us on Instagram. For me, Coach Juan, and for Jack at Deltoid Factory. And as always, if you have any questions, just leave them down in the comments below and I'll do my best to answer them. See you guys next video.